My name is Lucio Narducci from Politecnico di Bari, and I'm chairing this first morning session. It's very nice to be on this stage. So, the first paper we have in this session, we have four papers. The first one is Touch the Core, exploring task dependence. The speaker is
Hello, good morning, everyone. My name is Xing. I'm from Financial Technology, Tencent. I'm very pleased here to present our paper, Touch the Core, Exploring Task Dependence Among Hybrid Targets for Recommendation. We first consider some typical user behaviors in online business platform. In video sharing platform, such as TikTok, a video is exposed to user. Then user decide to click and view the video. Finally, the watch time is the key metric for the platform. As in our fund investment platform, 理财通, funds are exposed to users. User will decide to click and then buy one fund. The capital users spend in our platform is very critical. For these two examples, we can have some observations. First, task dependence are among these tasks. Second, we can notice that CTR, which is the click-through rate, and the CVR, conversion rates, are no longer the ultimate target. Actually, we consider how to learn the core target effectively here. A possible solution to this problem is multitask learning. There are several challenges we need to notice here. First, MTL aims to model implicit relationships among tasks. In our problem, relationship is explicitly dependent on each other. Second, the divergence exists. Usually, our core targets are continuous value, where the preceding targets are discrete. A user buying a fund will not indicate that she will invest much money in our platform. So we need to design an architecture to explore the task dependence both implicitly and explicitly. This also leads to another important issue: how to train such a model in a more stable way. Let's take a step further. When the targets are all discrete, previously sequential dependence MTL, which is SDMTL, can model the task dependence. However, as this formula indicates, it must certify that the prediction of task I equals it must certify that prediction of task I minus 1 subtract prediction of task I equals joint probability that task I is 0 and task I minus 1 is 1. This cannot hold anymore in our hybrid target learning. Hence, our method should model task dependence and model the task when the targets are hybrid. And we also need to optimize the MTL architecture. Let me formulate the problem here. Given features X and multiply target labels Y, we formulate the task predictions considering task dependence. Here, the first task Y hat I equals a function fxi given parameters theta. The final task y hat it equals fx given theta and the previous target labels. These are all classification tasks. Then the core target prediction is based on theta and all the preceding labels. And this problem is regression task. The object loss is regression loss and all other classification loss. And the last equation is the gradient, include both two parts. Here is our proposed framework, HTLNet, short for Hybrid Target Learning Net. The right tower predicts the core target, and the other towers learn preceding tasks. Inputs to tower T has 3 shared information. Embedding tensor for shared embedding layer. Representation ft-1 is the implicit information for preceding tasks. And the label embedding ft-1 is the label information for preceding tasks. Output is totally different between preceding target and the core target. The former one is optimized by cross-entropy loss, and the latter one is usually mean-squared error loss. The key unit here is LEU, label encoding unit, and IFU, information fusion unit, and I will describe it respectively. The first one is label encoding unit. It aims to encode the label information explicitly. However, discrete label cannot directly be delivered to continuous target as CVR prediction. Meanwhile, we only have the true label information in training stage, while the label information is unavailable in test stage. So we designed this unit by introducing map the label to the embedding tensor. And we also sampling label with the Gamble softmax operation to avoid use the true label. After we get both explicit label information and implicit representation for preceding tasks, we design the information field unit. Here, we introduce attention mechanism to adaptively learn the weight of preceding tasks and fuse them into a single tensor. The last issue is how to train our HTLNet. On one hand, the loss of continuous target is different for discrete targets in magnitude and direction. On the other hand, all the label embeddings and task representations will be transferred to the core target tower, which means core target loss will influence the optimization of other tasks with the gradient back propagation. Now we consider the gradient of task T+1. There are 3 factors affected: y hat T, and representation T, and shared embedding. To avoid too much influence, we cut off the gradient back propagation to y hat T and representation T. After that, only shared embedding transfer information among these tasks. Then we introduce 2 operations on the gradient of shared parameters between preceding tasks and core tasks. There are direction and magnitude respectively. The whole process is shown in this table. We conduct our experiment on 3 datasets. Quailian is a video dataset. Revalue is a shopping dataset, and our private dataset is collected from our fund investment platform. Here are some statistics of these datasets. The baseline here are divided into 3 types: single model, MTL model, SD-MTL model, and optimization method. Metrics here for regulation, we consider NRMSE and NMAE. For classification, we consider AUC and log loss. The results are shown here. The first insight is MTL models performs better than single models, and our HTLNet performs best. This justifies that's why we introduce MTL here. The second insight is SD-MTL model and the optimization method performs better on preceding tasks. This indicates that explicitly explored dependence is necessary, and the optimization strategy is very important. The third insight is general MTL model perform better than SD-MTL models on core target. We think this is because SD-MTL model mainly consider discrete targets, and the way to explore the targets will degrade the core target prediction. We also conduct aberration here. It's easy to see that both architecture and optimization are important. Especially without optimization, the performance decreases more. Next, we investigate more carefully into these two parts. We first investigate the influence of different components of the architecture. We remove some information of preceding tasks. It can see that removing any preceding information from the architecture will degrade the performance. Then we compare different infusion in IFU. It proves the attention is better than linear. Then we investigate optimization strategy. All three operations are effective. We also compare our strategy with other two general optimization strategies, gradient surgery and meta balance. It can be concluded that our method is superior and justify why we also design an optimization strategy for our HTLNet. The right finger also illustrates our gradient of co-targets really converges. We also deploy our HTLNet on our platform. We conduct A/B tests in a fund recommendation sincerely, only Caitong. The online metrics is click ratio, purchase ratio, and the purchase amount. We conduct the experiment in 2 weeks. The 2 weeks performance are shown in left. Finally, we summarize some limitations here. One is the training time cost. Our method actually needs some extra training resource. Then, as a reviewer suggests, we also deploy it in a long sequence dependence task. This is under our experiment. Finally, some techniques also can generalize to other cases, such as the label encoding unit can be generalized to convention-based prediction. Let me conclude our paper. Here, we identify the hybrid target learning in real fund recommendation and design HTLNet, including architecture and optimization strategy. Both online and offline experiments are conducted to verify our method. The below is a code link. After necessary company check, we will update it. Thank you for your kind listening. And the question is welcome.
Thank you, Xing Tang, for your presentation. So we have time for a few questions. There are 2 on Slido. The first one is the three-tower framework makes a lot of sense, but it is quite complex. How long did it take to evolve the framework to a final version?
Sorry, pardon. Actually, the tower aims to predict different targets. And our baseline is also an MTL model. So we need an extra type, but not too much. This will also, we have verified it by experiment, but due to the space limit, we omitted it. We will update on our GitHub website. Yeah.
Okay. The second question is more complicated because there are also some formulas. So, how does your idea compare to modeling using conditional probability, such as probability of revenue given purchase multiplied by probability of purchase given click multiplied by probability of click?
Yeah, but actually, when we do CVR prediction, we use this equation. But when we do hybrid tangent, we have a continuous distribution and a discrete distribution. It's hard to just multiply by it. And we also need an architecture to multiply both distribution. And so we find a label embedding to finish this work. Yeah.
Thank you. Any questions from the audience? Okay, no. Thank you very much for your presentation.